Okay, good afternoon, everybody. Let's come back to construction of Lebesgue measure again. So construction. On art D actually, but I will do some cheating. I will do only for D equals to 1. The bigger than 1 cases are actually similar, and it's actually much easier to understand this case quickly since we don't have much time. So let me first tell you that we are going to use the Riemann representation theorem. So you need a positive linear function to start with, which is defined on CC of R. In the last lecture, we have seen that some people had confusion about what is compactly supported continuous function. Compactly supported continuous function on a space, in our case, it will be real line. It would mean a function which is continuous on the whole of real line, but supported on a compact set. The misleading idea is, which we should avoid, that it is continuous just on the compact set. No, it is continuous on the whole space and supported on a compact space. Okay, the basic idea, as I said, is to use Riemann integration to define a positive linear function. But we have to define it in certain fashion. So for that, first let me tell you the basic idea of Riemann integration, which we are going to use very briefly. That suppose you have a closed interval, and suppose you have a continuous function defined on AP. Let's also assume f is real valued. For complex valued functions, everything can be done by writing f in terms of its real part and an imaginary part. Okay, now you start with any partition P, the standard way, say A0 equals to A. And no, let's not use this symbol. I will use a different symbol. Let's write A equals to S1, less S2, and so on, up to less Sn, which is equals to 2. So take a partition like this. Given this partition, I can actually define a positive linear functional, and I'm sure you will be able to recognize what that positive linear functional is. So I call it lambda p. Lambda p of f is simply defined as summation I from 1 to m minus 1, f at Si, then Si plus 1 minus Si. For all continuous functions f defined on AB, if I define like lambda pf by this formula, it's clearly a positive linear functional. Can you recognize what this object is classically called?
Riemann sum.
Exactly. This is the Riemann sum. And this is what we are going to use. It's not the UPF, LPF kind of description of Riemann integration. We are going to use the Riemann sum. And then one knows that if f is continuous, and if I define norm P to be equals to the maximum length of the subinterval, so it is maximum, Si plus 1 minus Si, such that 1 lesser equals to I lesser equals to m minus 1. Then if norm P goes to 0, that means the partition is getting refined and its length of individual subintervals are going to 0, then this actually implies that this lambda pf, which is a number, it converges to a number called the Riemann integral of f, that is integration a to b fx dx. This is a known fact. I have already assumed my f to be continuous. I am not going out of continuous functions. Now, it's almost this which we are going to use, but here the problem is there is some amount of arbitrariness with the partition P. One is not sure which partition one is working with. So what we want to do, we want to define partitions in a very systematic way. And that's why the set called Pn, which I defined in the last class, that is going to appear. Okay. Okay, so here we go. That the linear functional which we are going to work with. So take any f in CCR. Focus only in one dimension, that is R. Forget about RD for the time being. Then take any natural number n. Does anybody remember what Pn looks like in one dimension?
m by
Okay.
2 to the power n for n integer.
Excellent. K by 2 to the power n, where k integer. So what it does is it divides the whole real line into countably many points. And coming out of this omega n, or something called omega n, it's a collection of intervals of certain particular kind. They look like k by 2 to the power n, and then k plus 1 by 2 to the power n. That means length of each interval in omega n is 1 by 2 to the power n. And this, you simply take k is in Z. What is obvious from the shape of these intervals, that this gives you a countable disjoint union of the whole real line. This is a countable disjoint union. This is because of the nature of left close, right open. And as I said in the last class, the higher dimensional versions are actually cubes of side length 2 to the power n, which is in some sense left closed, right open. In 2 dimension, you can actually visualize them. Okay. So once these omega n's and pn's are formed, just notice one thing, that norm of omega n, because omega n gives you actually a partition of this real line, this goes to 0 as n goes to infinity. This is simply because the length of each subinterval appearing in omega n has length 1 by 2 to the power n. That is one thing to remember, though what I have written is technically incorrect because omega n is not really partition. It is actually coming from Pn. So if I write Pn instead of omega n, perhaps that will be better. That is the first thing to remember. Second thing is, how do you get omega n plus 1 from omega n? So omega n plus 1 is obtained from omega n from omega n. Tell me how? Anybody?
Inserting the midpoints.
Exactly, inserting the midpoints. And that is what you go on doing. So this is my way of refining a partition. Okay, that's a very systematic way. I start with a fixed interval, let us say omega 1. That is the first generation of partition of the whole real line. The next generation means inserting the midpoints. That gives you omega 2. The third generation is again inserting the midpoints and so on. Okay, so this is my way of refining a partition. This is a very systematic way of doing it. Okay. And now I define my positive linear function, which depends on n. So I define lambda nf to be simply as 1 by 2 to the power n summation x in Pn fx. Even without understanding what this sum actually means, let's quickly check whether this sum makes sense. Why does this sum make sense? How many points are there in Pn?
2 to the power n minus r.
How many points are there in Pn?
Oh, 2 to the power n minus 1. Oh.
So you think Pn is a finite set?
No, sorry, sir.
It's a countable infinite set such that distance between any two consecutive points is 1 by 2 to the power n, correct?
Yes, sir.
So how many points of Pn can be there inside the support of the function? F is in CCR. Fix n. If you fix n, there can only be finitely many points inside the support of F. And hence, the sum which is written here is actually a finite sum. And hence it makes sense. Now, can you identify this as Riemann sum? Sure, because this 1 by 2 to the power n has nothing to do with the sum. It can actually go inside the sum. So if you look at the omega n above, which is written here, if I ask you that I give you a compactly supported continuous function f, think of omega n as partition of the whole of real line and construct a Riemann sum out of omega n. What will you construct? Have you understood my question? That this collection omega n, which I have written here, this gives a partition of the whole real line. So in particular, it gives you a partition of any interval, any closed interval, which contains support of A. Correct? Now, out of that partition, suppose I want to produce a Riemann sum. Will it look like lambda n f? What it should be, if I want to create a Riemann sum out of omega n, it should be sum of the points which are included in the partition. In my case, these are certain k by 2 to the power n, finitely many. I have to evaluate the function at some point of the subinterval, then multiply by the length of the interval, correct?
Yes, sir.
Now, the length of the interval is always 1 by 2 to the power n. Doesn't matter which point is, because I'm keeping n fixed. Correct? The length is 2 to the power 1 by 2 to the power n for every k. So from that definition of the Riemann sum, which is value of the function at a point times the interval, and then the sum over the partition, the length of each interval is constant here. It is 1 by 2 to the power n. So it comes out of the sum. And what you are left with now is a point. Which point you will like to choose? Well, I am choosing points only which is the left-hand point. Okay. So this x is actually some k by 2 to the power n. This is actually some k by 2 to the power n. Am I making sense? Is this clear to you what I'm trying to say?
Yes, sir.
So all I am trying to say is that this lambda n f, which I have defined here, is nothing but Riemann sum corresponding to the partition Pn. Okay, so this is Riemann sum. Corresponding to Pn. Okay. Now, this is for one. Now, if I want to approach Riemann integration, I have to vary my n because I have to make my interval smaller and smaller because refinement will be needed. So I will bring in other n's also. Okay. Now, just notice one thing, that in this definition of lambda nf, it is not really the continuity of the function which matters. The function could actually be discontinuous. What matters is that the support of the function must be compact. If that happens, then I can define lambda nf. Okay. The support compact is needed, otherwise the sum could be infinite and you could land into a problem. Okay, now let us specialize further. Suppose f is real valued in CCR, and let us say support of f is sitting inside some open set W. Let us call it open interval. That is what was actually my notation. W was always the rectangles. So in one dimension, it is an interval. Okay. So let us say W is of the form alpha beta. Now, this is not a weird thing to say because after all, the support of the function is compact. So that set is closed and bounded. So I can always find an open interval on which the support of F actually rests. Now notice, now what I'm going to do is I'm now going to produce two interesting functions called G and H. They're somehow connected to F exactly the way you deal with things in the UPF LPF definition of Riemann integration, looking at minimum and maximum. That is exactly what I'm going to do. Those minimums and maximums, which you called UPF and LPF, they actually give rise to certain step functions. So that is what actually I'm aiming at. But notice one thing, that F is uniformly continuous. Is this clear to all of you?
Yes, sir.
Why it is uniformly continuous?
Continuous function on compact set.
It is continuous and it is supported on a compact set, so it is obviously uniformly continuous. Fantastic. So give an epsilon bigger than 0, fix it, get a delta bigger than 0, such that the standard definition applies that Fy minus epsilon is less Fx less Fy plus epsilon. If mod x minus y is less than delta. Now what I do is, I do the following. I choose n, a big N, such that 1 by 2 to the power n is strictly less than delta. And I'm now going to look at semi-open intervals whose length is 1 by 2 to the power n. So I say you better consider this. So consider first omega capital N. So everybody here is of the form k by 2 to the power n, k plus 1 by 2 to the power n, where your k belongs to Z. I got this omega. Okay. Now, I want to define two functions G and H for you, but for that, I think it is better to draw a picture. So here is the picture. This is your whole real line. Let's draw a big picture. Suppose this is my alpha. Suppose this is my beta. My function is supported inside this alpha and beta. Now, omega n is decomposing whole real line. So it is also decomposing this alpha and beta. And let's try to draw three typical intervals from omega n, which are going to appear in our discussion. One of them maybe is of this form. One of them maybe is of this form. And one of them is of this form. Do you agree that these are the only typical cases which can arise with the intervals which coming out of omega n?
Yes, sir.
I made a mistake. It's open there. Okay, so these are the cases. So let's give a name to them. Call this, say, I1. Call this I2. Call this I3. Now, can you tell me if I take 2 points x and y, let us say in I1, what will be mod of fx minus fy? Is the question clear? Suppose I take x and y inside the interval I1 drawn in red. What can I say about mod of fx minus fy? What is the length of this interval I1?
Less than epsilon.
Yes, it's less than epsilon because the length of this interval is 1 by 2 to the power n. And 1 by 2 to the power n has been chosen in such a way that it is less than delta. So by uniform continuity, if you choose any 2 points, x and y in I1, mod of fx minus fy is less than epsilon. The same applies to I2, same applies to I3, because all these intervals are of same length. Okay, so far? We now quickly define G equals to simply minimum of f on each interval coming from omega capital N, and define H to be equals to maximum of f. I can do that because my f is real valued on each interval coming from. If I do that, then the following happens. So you understand that your G is basically a step function, right? On a given interval, the height of G remains same. On a given interval, the height of H also remains same. So what we have then got is the following. I write them as 1, 2, 3. G and H are constant. On each semi-open interval arising in omega n, omega capital N, that is what I'm working with. Number 2, G is lesser equals to F, lesser equals to H, because I looked at the maximum and minimum. There is surprise here. Number 3, and that's important, H minus G is always lesser equals to epsilon. That is because of the uniform continuity, that fx minus fy is always less than epsilon. And number 4, that's important, G and H are supported in, now I want to test how much you have understood. Supported where? Look at the picture. So can you tell me where G is supported, where H is supported? There are many more intervals which I have not drawn. I have drawn some extreme cases. Support of F is some compact set inside the interval alpha beta. So can you tell me where is support of G, where is support of F? For example, let us look at I1. Okay. So what do you think will be the about support of G? If I look at this region, what will be the value of G here?
Zero.
What is the value of F there?
0.
So what is the value of G there?
0.
Now I look at this small extra left out portion here. Okay. So what is the value of F here? I mean this portion on this line. What is the value of F here?
0.
Because beta is before that. So what is the value of H there? That is 0. That means G and H both actually supported inside this open interval alpha beta, which I call W. So they are supported in W. Fantastic. I got a picture about G and H. Okay, I'm going to use them crucially. Now, if N is bigger than capital N, define lambda NF. Define lambda NF. Exactly the way we are doing, but don't change G and H. Don't change G and H. They remain same. So you just define lambda NF accordingly. So it follows then that if N is bigger than or equals to capital N, then the following thing happens. First of all, lambda NG since G is lesser equals to F, this is always lesser equals to lambda in F. The way lambda in F is defined, it is sum of the function at the points times length of the interval. And F is always bigger than G, so this happens. Similarly, this is also lesser equals to lambda in H. Now, since I did not change G and H for other values of N, it turns out that this is same as equals to lambda big N G. That doesn't change. And so is this. Okay. This is because according to the subdivision, I did not change my G and H. They were kept fixed. So once they were constantly defined at the capital N generation, they remain so all for the next generations. And hence lambda capital NG is same as lambda small ng. And same thing applies for H. The advantage at this point is to note the following, that for all n bigger than or equals to capital N, if I look at lambda in H minus lambda in G, suppose we look at this, what happens? Well, I can write down the definition and try to see what happens. Well, so this is then 1 by 2 to the power n summation over Pn Hx minus Gx. Okay. So what happens in this case? Well, Hx and Gx are basically maximum and minimum value of the continuous function. So by uniform continuity, as long as I am within intervals of length less than delta, which is going to be the case because this would imply that 1 by 2 to the power n is also strictly less than delta. So this quantity is always less than epsilon. So we will see that it actually turns out to be lesser equals to epsilon times length of the whole interval which you are working with. Okay. Okay, so far. Is this okay or it's not?
It's okay, sir.
Okay. So what does that imply? The difference between lambda ng and lambda nh, these two quantities, is at most epsilon times b minus alpha. So I say that this implies that limit superior of lambda n, the distance between limit superior and the limit inferior, these are basically limits of certain subsequences. This also has to be less or equals to epsilon into b minus beta minus alpha. But here epsilon is arbitrary. So that would imply limit superior lambda n is actually equals to limit inferior lambda n. That means that since limit superior and limit inferior are same, it actually implies that limit n tending to infinity, lambda nf exists because lim sup and lim inf are same. This is what we call lambda f, the linear functional I'm searching for. But if you have carefully followed what we have done and what I mentioned about Riemann sum, you actually already know what this limit is. Can anybody guess what this limit actually is? Limit n tending to infinity lambda n f. Anybody? Can you guess what that limit actually is?
Riemann integral?
Exactly. It's actually the Riemann integration of the function over the whole of real line. And again, the moment I write that, people get confused because Riemann integration is always done over bounded regions. I say here it is actually over a bounded region. It is nothing but integration alpha to beta fx dx. There is no problem because outside that the function is actually 0. So the positive linear functional I'm searching for is actually this guy, and it is actually the Riemann integration of the function. But to understand why it is Riemann integration, you don't really need to know what is Riemann integration. All we are doing is just using Riemann Sum. And I can do exactly the same thing in higher dimension because Riemann integration makes sense there. But the point is, since lambda n f is bigger than or equals to 0 for all n, so this also implies lambda f is bigger than or equals to 0 if f is bigger than or equals to 0. So this defines a positive linear functional. And hence, by Riesz representation theorem, it gives rise to a measure. That measure is called the Lebesgue measure. So now I write down the statement of the theorem. It's a long statement. It contains everything, but surprisingly, the proof is not long. So theorem. There exists a positive complete measure mu. No, not mu. I will call it M. Defined on a sigma algebra. M on R. This sigma algebra is called the Lebesgue sigma algebra, such that it has many interesting properties. The first and foremost, the most important property is measure of any interval V is length of V. That's the first important property. And this should be true for every interval V. So this measure actually generalizes the length of an interval. B. Capital M, the so-called Lebesgue sigma algebra, contains B, meaning the Borel sigma algebra. Okay. In fact, I'm telling you in advance, I don't know whether I'll be able to prove it or not. Lebesgue sigma algebra, M contains a huge number of sets, huge. Its cardinality is at least 2 to the power C, where C is the cardinality of the reals. Whereas Borel sigma algebra is comparatively, if you start counting how many sets it has a smaller number of sets. It's just uncountable. That is cardinality of the reals. So in other words, there are a huge number of Lebesgue measurable sets which are not Borel measurable. Okay, so M contains B more precisely. We can actually have a more precise notation. Measured theoretically, actually difference is not much. I will tell you why. More precisely, a set E belongs to M if and only if there exists a set A, which is F sigma, and a set, say, B, which is G delta, such that E is sandwiched between A and B, and Lebesgue measure M of B minus A is actually equal to C. Now, what is the consequence of this fact? The consequence of this fact is if E is in the Lebesgue sigma algebra, capital A, capital M, you can always write E to be equals to A union E minus A. Now, A is an F sigma set. That means it is countable union of closed sets. That means it's a Borel set. And can you tell me what is measure of E minus A?
0.
Excellent. But why I can apply the measure on this set? Is it this E minus A is in the sigma algebra M? Of course it is. Or no, it's not clear. It's clear, F is in B.
Yes.
Is E minus A in B, in M? Is it a Lebesgue measurable set?
Yes.
Why?
E is Lebesgue measurable. A is Lebesgue measurable. Therefore, E minus
That
A.
is one part. That is, if E belongs to M, then this happens. Suppose I give you A is an F sigma set, B is a G delta set, E is squeezed in between, and measure of B minus A equals to 0. From this data, can you say that E belongs to M?
Yes, because completeness of Lebesgue measure.
Exactly. The completeness. The measure is complete. That means if you have any set of measure 0, all its subsets are in the sigma algebra. So F is in B, E minus A belongs to M. So that is what I wanted to mean when I said that difference between B and M, as far as cardinality is concerned, is huge, but not measured theoretically. In the sense, if you take Borel sets and go on adding measured 0 sets with it, you will actually get the whole Lebesgue sigma algebra. So the difference between a Lebesgue measurable set, that means elements of the Lebesgue sigma algebra, and difference between a Borel measurable set, that is element of the Borel sigma algebra, is basically a set of measure 0. Okay, so measure theory, I mean close. Same is not is an incorrect word. Measure theoretically they are close, but not set theoretically. And one actually knows that Lebesgue sigma algebra is strictly larger than Borel sigma algebra. That there are sets in M which are not in B. Okay, that is my property B. C is a more interesting property, that M of E is M of E plus X. And this is true for all E in the Lebesgue sigma algebra M. We call that the Lebesgue measure M is translation invariant. This is what we mean by translation invariance, that if you translate a set by an X, the measure does not change. And then the property D, which is more interesting, that suppose you have a measure mu, which is positive measure. Well, for you, perhaps measure always mean positive. So let's not write positive. Suppose mu is a measure. And translation invariant. No, suppose mu is a translation invariant Borel measure. Let's write that. Translation invariant Borel measure. That means it's defined Borel structure. If measure of every compact set is finite, for all K subset of R compact, they're all Borel sets, then there exists a positive real number C such that mu of E is equals to C of E, C of M for all E subset of R Borel. So what we mean is that you take any translation invariant measure or any translation invariant Borel measure, which has the property that it is finite on all compact sets, then that measure is just a constant multiple of the Lebesgue measure. There is no other measure which has this property except constant multiple of Lebesgue measure. Now, there is little bit of care which is needed here, that suppose I define a measure the following way on the Borel sigma algebra of real line. Let us say mu of E is infinity for all Borel sets E. That then obviously is a measure, because measures can be extended real value. It is also translation invariant because for every set it is infinity. That is not a constant multiple of Lebesgue measure, and that is the importance of this property. That infinity on every set you cannot take. So good measures has this property that it should be finite on compact sets. So this result is saying any translation invariant measure which is finite on all compact sets is nothing but a constant multiple of the above measure. Last property. This is not much in one dimension. So if you define Tx equals to alpha x for some alpha in R. Then measure of any set from E, if you apply T on that and measure it, and if you look at measure of E, then there should be a number appearing here depending on alpha. That number turns out to be modulus of alpha. And that is true for all E in. This is what we are going to prove. Are the statements clear to all of you?
Yes, sir.
One by one. First important property, measure of every interval is length. Second important property, that M contains B, and I should also add here that is most important, M is regular. This is very important. Third property is that the measure is translation invariant. Fourth property is that any translation invariant good measure, that is finite on compact sets, is a scalar multiple of the Lebesgue measure. And the third property is a transformation rule. It has a higher dimensional version also. So let me quickly mention that here. We are not proving it. So suppose you have a linear map T from RT to RT. It's a linear map. Then measure of TE is equals to 0 if dimension of the image of RT under T is less than T. It's actually modulus determinant of T times measure of T if dimension of T at T is equal to T. Okay. So this is a higher dimensional version of this last result, which we are not going to prove. It's not very difficult to prove it anyway. So let's quickly get into the proof of the first one. I have only 10 minutes left. We are trying to prove that measure of any interval is its length. So given any interval alpha, beta, let us say, so what is length of any interval AB, we know is B minus A. And instead of open interval, you take closed interval, semi-open interval, doesn't matter. Its length is always B minus A. So let us start with any interval. So W, say it's an open interval. Because this part of the proof is slightly complicated. And let us say ER be the closure of the semi-open intervals from omega R, which are, should I say which are or which lies in the. So what I'm saying is that you fix a generation omega R of cubes, in our case intervals, semi-open intervals, they partition the whole real line. Take W to be an open interval. So some of those intervals are sitting inside. Those who are sitting inside take their closures. You actually get a closed interval. So you will get a picture like this. It's very easy to see. So this is your open interval W. It looks something like this. So ER may look something like this. It would be a closed interval actually. or maybe right side semi-open, but since you are taking closure, the right side will be closed. Okay. So let's ER closure. Let me use this symbol. Am I making sense? What I said? Have you followed? Is this clear what I said? Could you hear me?
Yes, sir.
Okay. Okay. So are you convinced that this is going to be a closed interval? Because remember how this open interval whole real line is getting broken. If I try to draw a picture, it would look like this. And so on. Right? So look at all those intervals who are sitting inside this open interval, big open interval, which I have drawn here. And then if you look at their closure, you are going to get a nice closed interval. Okay, call it ER closure. And then get FR such that this happens. ER closure, which is now a compact set, we can always do that. So let me draw what FR
Yes,
looks
sir.
like. It looks like this. It's 1, then dies down. Okay, this is the graph of my FR. Okay. Now, next, I then know that FR is a compactly supported continuous function and 0 lesser equals to F lesser equals to 1. We do know that because this is what Eurasian lemma supplies me. And now I define GR. This is something which I need to explain a little bit. It is maximum of F1, F, and so on, up to FR. Now, what do I mean by that? From where do I suddenly get an F1? I was talking only about FR. Well, you may not get F1 because the open set which you have started with, it could be very small. So it may not contain any interval which are in omega 1. That can happen. In that case, you will not get any F1. Forget them. Now look at omega 2. It may even happen that no interval of omega 2 is sitting inside your small open set. But from some level, it will start belonging because as generation progresses, the guys are getting smaller and smaller intervals. So at some stage, they will start entering. From that stage onwards, you will be getting FR. So at any stage for any R for which it does happen, I define GR to be maximum of FR and the previous generation FRs. Is my construction clear what I'm trying to say?
Yes, sir.
So what I'm saying is that suppose at R minus 1th generation, the intervals are sitting inside this interval, then you will get an FR minus 1. And for R, I am getting an FR. I will be looking at the maximum value of these guys. So here what I have written is with the understanding that from the first level onwards, they are sitting inside this open interval. That may not be true. So in that case, forget F1. There is no F1. Your maximum will then start from F2 onwards. Now you may say there is nobody from second generation either. I say ignore them. Start from F3 onwards. But you have to start at certain stage and go up to FR. That is what GR is. Point is that 0 lesser equals to GR lesser equals to 1 still remains true because it is true for FRs. And it is also true that GRs are increasing. That's important. But that's obvious by taking this maximum. And now let me look at the following scenario. I'm going to write lambda, the positive linear functional which I've defined. This lambda FR is certainly lesser equals to lambda GR. Okay. Now this GR, which is maximum of this function, it is always less than or equals to 1. Correct? This is here. right? GR is always less than or equals to 1. Now, how does one define lambda GR? Well, looking at its maximum, minimum, and then the Riemann sum kind of a thing. Now, in the Riemann sum, all those fellows which are appearing GRX, they are lesser equals to 1. That means it is lesser equals to the length of the supporting interval. But all those supporting intervals are sitting inside the set W, which I have denoted here as open interval. So this is actually lesser equals to length of W. If it is not clear, I can explain once again. It is actually true for all lambda n GR. Because for each n, I can talk about lambda n GR, right? What is lambda n GR? It is the value of GR at a point and then time. It times the length of the subinterval, and then you sum over the intervals. Now, this GR is supported inside my, I said V, but I should actually write W. Maybe that's why you are confused. Now, all those subintervals using which you are defining lambda n GR, those subintervals are all sitting inside W. And on that subinterval, the value of lambda GR is simply the length of that interval. If you look back at my description of lambda n, I can scroll up. You will actually be able to see. It's actually very easy. Where is defined? The value of the function at a point, if you take your GR, that is lesser equals to 1, summation, and then it is the length. So all these lengths are actually adding up, giving the support of GR. And all these things are happening inside W. So the total lengths which are counting is actually lesser equals to the length of W. That is what I had written. And obviously, since FR is equals to 1 according to the picture on ER, this is your graph of FR, which is lesser equals to GR. And FR is 1 on this whole set, which is ER. It's clear that this lambda FR is bigger than or equals to length of ER. Okay, this comes straight away from the definition of the positive linear function of lambda. And if you think of it as a Riemann integration, it is actually much easier. You are simply saying FR is bigger than or equals to 1. So integration over ER, FRx dx is bigger than or equals to integration over ER of the constant function 1 dx, which is nothing. I'm almost there. Now, as R goes to infinity, where does this length go? Well, if you again look back at the picture, if you choose smaller R now, then many more subdivisions will appear. If you choose smaller subdivisions, more sets will start appearing. So the length of these sets are actually going towards the length of W. Because more subdivision means you are allowing more intervals to come in. So this actually goes to length of W. On the other hand, where does GR? I know it's an increasing sequence of functions. So take any X in W. What is W in this picture? In this picture, where is W? Who is W?
W, the open interval.
Exactly, the open interval is W. Now take any X anywhere. Now that X belongs to some ER closure, right? Now on ER closure, FR is actually equals to 1. That means GR is also equals to 1 there, because GR is bigger than FR and lesser equals to 1. So for every x, as you take R towards infinity, these GRXs are actually increasing to the indicator function of W. So GR actually increases to chi of W. This implies, by monotone convergence theorem, integration over R, GRX DMX, that is the measure which came out of the Riesz representation theorem. So did I tell you that, what I did? So once again, I have first defined the positive linear functional lambda for you. By Riesz representation theorem, it gives rise to a measure little m and a sigma algebra capital M. Since R is sigma compact, this measure little m is already regular, and by the previous properties, B is actually done from Riesz representation theorem. We are struggling to prove A. So Riesz representation theorem gave me a measure M. So monotone convergence theorem applies to that measure. And since this sequence of functions are increasing, I actually get integral over R chi W x dmx. But that, by definition of integration, is nothing but M of W. Okay. Now look at the upper inequality here. You know that this length ERs, they are going to length of W. That means this guy, this lambda GR, that is also going to W. Correct? But what is lambda GR by this representation theorem? Can anybody tell me what is lambda GR?
Integration over R GR.
Yes. Integration over R, GR,
GR.
yes, X, then what should I write? DX or DMX? Riesz representation
DMX.
theorem gives
DMX.
rise to a measure.
DMX.
That measure we called M. So this integration, what should I write? GRX, DX or DMX?
DMX.
DMX. This is what lambda GR is. This is what Riesz representation theorem tells me. But I see from the previous line that this, well, it's not really equal to, it converges by monotone convergence theorem. So I apply MCT. So I see that this is equals to lambda GR. It converges to MW. So let's quickly write down here. What have I got? I got two things actually. I got that lambda GR going to MW. That is what I got from here. But the second thing I got from this line and this line, that length ER goes to length W, lambda GR is sitting in between. So lambda GR is also converging to length of W. What is your conclusion? All this is happening as R goes to infinity. Yeah, what is your conclusion?
MW is equal to length of W.
And that is what we wanted to prove. This proves A. This proves A. B follows straight away from Riesz representation theorem. In the next class, we'll prove C, D, and E. Okay, I have already overstepped my time. Sorry. So I'm quitting now.